Welcome to the 39th lecture of this course. Today we will discuss the topic of NP-Completeness. Okay. So, last time I mentioned that so there are these problems in NP which are in some sense the hardest problems in NP. So, how do we characterize these problems and how do we define hardness of a problem? Okay. So, that is going to be our agenda today. So, we have seen the definition of reduction, reducing one language to another. So, today we are going to fine tune that definition and talk about polynomial time reduction. Okay. So, let us say L1 and L2 are two languages. So, we say that L1 polynomial time reduces to L2, okay, and this is denoted as L1 with a subscript p if there exists a polytime computable function f from sigma star to sigma star such that x belongs to L1 if and only if f of x belongs to L2. Okay. So, the only difference is that, so we say that L1 polynomial time reduces to L2 if the function f is a polytime computable function. Okay. So, the difference is that, so we have a Turing machine. So, we say that a function is computable if there is a Turing machine that outputs the value of f of x when given x. Okay. So, now in addition, if we restrict the Turing machine to run for a polynomial number of steps in the length of x, then we say that the function f is polytime computable. So, that is the only difference. The rest of the definition is similar to that of reduction. Okay. So, now we say that, so let L be some language. Okay. So, L is said to be NP-hard if for all languages L prime belonging to NP, L prime reduces to L. Okay. L prime polynomial time reduces to L. Okay. So, in other words, we say that a language L is NP hard if every other language in NP, okay, or every language including L itself must reduce to L in polynomial time. In other words, there is a polynomial time computable function which map instances of L prime to instances of L. Okay. Now, we say that L is NP complete if L is NP hard and L belongs to NP. Okay. So, if a language is NP hard, it need not necessarily lie in NP. Okay. So, maybe it lies outside NP. So, that can very well happen. So, all we say here is that every language in NP reduces to L, but L can lie anywhere. But we say that it is NP complete if it is NP hard as well as it belongs to NP. Okay. So, this is our definition of the highest level of hardness inside NP in some sense. So, basically if one language, if we have an NP complete problem, if we have a language which is NP complete, then of course it belongs to NP by definition, and every other language in NP can be reduced to this language. So, what are some of the properties that we can say about NP complete problems? So, the first result is, state it as a theorem. So, if L is NP complete or even NP hard and L belongs to P, then P equals NP. Okay. In fact, this is probably the most popular strategy to show that P and NP are the same. You take an NP complete problem and you give a polynomial time algorithm for that problem. If you can do that, then we would have shown that P is equal to NP. And the proof is quite easy. So, the idea is as follows. So, basically take any problem in NP. Okay. So, let L prime be a problem in NP. Okay. So, because L is NP complete, it means that L is NP hard. So, we have that L prime reduces to L. Okay. And now, because L belongs to P, we have that L prime also belongs to P. The reason is, so suppose if I want to show that Y is L prime in P, so take a box. Okay, so this is a poly-time algorithm for L prime. So, given an input x, okay, so look at this reduction. So, this reduction is via some function f. So, via f say. So, first compute f of x. So, given x, so feed x to this box and then compute f of x. Okay. Now, if f of x, so what is f of x? F of x is an instance of the language L, okay, and our assumption is that L belongs to P. Okay. So, now I apply that box on top of this. Okay. So, let me make it bigger. So, I get f of x and then I apply the box for, so this is P algo for the language L. So, I apply the box to this. Now, if this guy output yes, then I output yes, and if this guy outputs no, then I output a no. Okay. So, if I am given an input x, I first convert it into f of x. F of x is an instance of L because of this reduction, and we know that L belongs to P. So, there is a polynomial time algorithm for L. So, now I just check if f of x is in L or not. If f of x is in L, I output yes. If it is not in L, I output no. And this total algorithm consists of two parts. First computing f of x and then applying the algorithm for L on f of x, and both these algorithms are polynomial time, hence the total box also takes polynomial time. Okay. So, this is a strategy to show that a problem, if you are able to, if you want to show that P is equal to NP, then here is a strategy to that one can use. Okay. So, now I will discuss a mechanism to show problems to be NP complete. Okay. And this theorem is similar to the way in which we showed that languages are undecidable. That is, if L1 polynomial time reduces to L2 and L1 is NP hard, then L2 is also is also NP hard. Okay. So, if I have a reduction L1 to L2 such that the first language is NP hard, then it implies that the second language is also NP hard. Okay. So, to prove this, what I will do is I will use a lemma. So, this is again a lemma that is of interest by itself. Okay. So, suppose we have three languages L1, L2 and L3. So, if okay, so let L1, L2 and L3 be three languages. So, if L1 reduces to L2 and L2 reduces to L3, then L1 reduces to L3 also. Okay. So, in some sense the reduction is transitive in nature. So, if 1 reduces to 2 and 2 reduces to 3, then 1 reduces to 3. Okay. So, how do we prove this? So, suppose that L1 reduces to L2 via a function f, and L2 reduces to L3 via a function g. Okay. So, now I want to reduce L1 to L3. So, I have to give a function. Okay, I have to give a function. So, what is the function going to be? So, this function is going to be nothing but a composition of f and g. Okay. So, first, given an input x, I apply f to it. Okay. So, this is my box f. So, this produces f of x. Okay. So, observe that if x is in L1, then f of x is in L2, and if x is not in L1, then f of x is not in L2 by the definition of reduction. Now, I feed f of x to the box for g. So, g is also a polynomial time computable function. So, there is a polynomial time algorithm for g, and this will give me g of f of x, and I just output this as the answer. Okay. So, let us call this as h of x. Okay. So, define h of x to be g of f of x, and therefore, L1 reduces to L3 via the function h. Okay. Why is that? So, take an x which belongs to L1. So, if x is in L1, then f of x is in L2. If f of x is in L2, then g of f of x is in L3. Hence, that is the same as h. So, therefore, h of x is in L3. Okay. So, if x belongs to L1, then f of x is in L2, which implies that h of x will be in L3. On the other hand, if x does not belong to L1, okay, then by the definition f of x will not belong to L2, okay, is not in L2, and if f of x is not in L2, then g of f of x is not in L3, therefore, h of x is not in L3. and why is H computable in polynomial time? So, we also have to prove that. So, note that H is nothing but applying f first and then g. Okay. So, this takes some polynomial number of steps, this takes some polynomial number of steps. So, the total is some other polynomial. Okay. So, H is polytime computable since f and g are polytime computable. Okay. So, now we will use this fact to prove our theorem. So, this was the lemma that we showed. So, this is the proof of the lemma. Now, let us go back to the proof of this theorem. This is what we want to show, that if L1 reduces to L2 and L1 is NP hard, then L2 is also NP hard. Okay. So, what I have is, so what I want to show is that L2 is NP hard. Okay. So, let me call this proof of, let us give this a name, theorem 2. So, proof of theorem 2. Okay. So, take any language in NP. So, let L prime be a language in NP. To show that L2 is NP hard, I have to show that L prime reduces to L2. Okay. So, now take, we have a language in NP and we know that L1 is NP hard. Okay. So, we have that L prime reduces to L1, okay, since L1 is NP hard, and of course, we also have another statement that L1 reduces to L2. Okay, we have that L1 reduces to L2. So, this is our one of the hypotheses, or not call it hypothesis, I will just call it assumption. So, now we apply the lemma that we have L prime reduces to L1 and L1 reduces to L2. So, therefore, combining both these, we have that L prime reduces to L2. Okay. So, this proves that L2 is NP hard as well. Okay. So, this is what we actually wanted. So, now we have a mechanism to show languages are NP hard, but then we need a first NP hard problem, okay, because we need to. So, to show that language is NP hard, I need to at least pick some NP hard problem and then reduce, give a reduction from that problem to my given problem. Okay. So, what is the first NP hard problem? Okay. So, this was a famous result again in computer science due to Cook and Levin. So, this is called the Cook-Levin theorem. Okay. So, they actually independently proved the following, that there is this problem called the satisfiability problem. SAT is NP hard, and also it is in NP. So, what it implies is that SAT is NP complete. Okay. So, what we will do next is that we will look at the definition of this problem. So, what is the satisfiability problem? Okay. So, remember that to show the first language to be NP hard, we have to somehow argue that every other language in NP reduces to this language. Okay. So, there can be infinitely many languages in NP and we cannot do it one by one. So, we have to give a generic strategy So, the strategy was to take a NP machine, okay, take any language that is in NP, consider the machine for that language, look at its configurations, how they behave, and using that somehow argue that this problem SAT is NP hard. Okay. So, let us first understand what the problem SAT is. So, the Boolean satisfiability problem. Okay. So, a Boolean formula is a formula defined inductively over Boolean variables and the gates and or and not. Okay. So, I am not going to give the precise definition of what a Boolean formula is, okay, but I am going to give it with an example. So, I am assuming that you have seen what a Boolean formula is at some point of your curriculum, but if not, I would suggest that you go back and refer to it, find out what is the exact definition. But what I am going to do is I am going to give some examples which would make it clear. So, here are some examples of Boolean formula. So, it is basically a formula that is defined over Boolean variables. Boolean variables are variables that can take only two values, 0 and 1, and gates and or and not. Okay. For example, I can have something like x1 or x2 bar and let us say x3. So, this is a Boolean formula. Okay. So, x1, x2 and x3 are Boolean variables, and I have, so this is a OR gate, this is an AND gate, and this is a NOT gate. Okay. So, I can also have another formula, let us look at another formula, x1 or x2 bar and x3 bar or x1 bar and x2 bar or x4. Okay. So, here I have a Boolean formula that is defined over 4 variables. So, there are 4 variables x1, x2, x3 and x4, and it is written in this manner. Okay. So, it is defined. So, basically I said inductively because at the base level the variables are also Boolean formula, and then I combine Boolean formula with the help of the Boolean operators. Okay. So, the OR of 2 Boolean operators is a Boolean formula, AND of 2 Boolean formula is a Boolean formula, and NOT is a operator which takes only one argument. So, NOT of a Boolean formula also gives a Boolean formula, and I use brackets to define precedence. Okay. So, which part gets precedence. So, this is similar to arithmetic expressions also. So, now I will define what is a truth assignment. A truth assignment tau is an assignment of values 0 or 1 to each Boolean variable. Okay. For example, if I look at, let us say if I look at a truth assignment tau, which is defined, which is giving, let us say x1 equal to 0, x2 equal to 1, x3 equal to 1 and x4 equals 0. So, under this assignment, what is the value of this Boolean formula? Okay. So, because x1 equal to 0 and x2 equal to 1, so the first argument, I mean this the Boolean formula within the first parenthesis, so x1 is 0. So, let me write it down. So, if I have x1 or x2 bar and x3 bar or x1 bar and x2 bar or x4. So, x1 is 0, x2 is 1. So, x2 bar will be 0. So, this is 0 or 0 with x3 bar is 0, x1 bar is a 1, okay. x2 bar is a 0 and x4 is a 0, lot of zeros. Okay. So, now if I evaluate this, so this is so 0 or 0 is a 0, 0 or 1 is a 1 and 0 or 0 is again a 0. And now I have AND of 0, 1 and 0, which is equal to 0. Okay. So, under the truth assignment, so under this truth assignment, the Boolean formula evaluates to 0. Okay. So, we say that a Boolean formula phi is satisfiable if there exists a truth assignment tau such that phi of tau evaluates to 1. Okay. And now we can define the problem SAT. So, SAT is basically the set of all formulas phi such that phi is satisfiable. Okay. So, we can define a few more things, we can define another language as well. So, let me define it here. A literal is a variable xi or xi bar. So, it is a variable or its complement. A clause is an OR of literals. Okay. For example, in this Boolean formula, this is a clause, this is a clause and this is a clause. A 3CNF formula is an AND of clauses where each clause has 3 literals. Okay. For example, this is a 2 CNF formula, because each clause, note here, has 2 literals. This one has 2 literals, this one has 2 literals, and the third clause also has 2 literals. Similarly, if I have 3 literals, it is called a 3 CNF formula. And now I can define another problem which is similar to the satisfiability problem. It is known as the 3 SAT problem, which states that phi such that phi is a 3 CNF satisfiable Boolean formula. Okay. So, this is a variant of satisfiability where the Boolean formula is restricted to be a formula which has this particular form. So, it is a 3 CNF form. Okay. So, I will stop here today. We will continue more on NP completeness in our next lecture. Thank you.